So today we're going to talk about streaming algorithms. In fact, we're going to talk about a couple algorithms which are randomized. They're randomized Monte Carlo algorithms, so that'll tie in well with the last lecture on randomized Monte Carlo algorithms. And what are streaming algorithms? Basically, algorithm must process a stream of incoming data, then be able to answer some query or family, or like many different queries. Okay. And the goal here usually is to use very little memory. In particular, I don't want to remember most of what I saw. And if you want to learn more, take my graduate course, CS294-165, in fall 2020. So we'll have, it won't just be about streaming, but streaming will be a large component of that course. And I mean, you can also think really of streaming algorithms as being dynamic data structures, right? What is a data structure? What is a data structure? A data structure is just a way of laying out data in memory such that you can efficiently query it. What is a dynamic data structure? A dynamic data structure is a data structure where you're allowed to update the underlying data set. You're allowed to change something in the data set or insert a new item in the data set or delete some item from the data set, right? So when I say stream of incoming data, you should, each basically token in the stream is updating my data set, right? Like, for example, I'm seeing a new data item. And then I want to be able to answer queries. That's exactly what data structures do. So really, you can also view streaming algorithms as really dynamic data structures that use very little memory. Like they don't remember most of the data set, right? Usually, we always in this class have assumed that you always have at least linear memory and you can actually remember the input. But here what I'm saying is you can't remember the input. You don't have enough memory to remember the input. So a very simple example. Let's say I'm an online vendor. And each stream item is a sale with a dollar amount. And my query is return the gross revenue so far. Okay. That's very simple. Here's a simple algorithm or simple data structure. Just keep a counter. Initialized to 0. Right? So at the beginning of the day, my gross revenue is 0. I haven't sold anything yet. Every time there's a sale, I just look at the sale price, and I just add that into the counter. So this counter is maintaining my gross revenue for the day. Now, am I remembering most of what I saw? No, I'm using very little memory. I only have basically one int in my memory. I don't need to remember the actual data set, the actual list of all sales that happened to be able to answer this query. Okay? So this is just to give you something tangible right away, so you can realize, oh, okay, this is not that abstract. This makes sense. But now I want to talk about a couple of problems where the algorithm is not so simple. And before I do that, I had a probability review on last lecture. And we talked about linearity of expectation and Markov's inequality. I will need just one more inequality for today. And then that inequality is Chebyshev's inequality. So x is some random variable. And it says it's like for all t greater than 0, the probability that x deviates from its expectation by more than t is at most the variance of x divided by t squared. And if you don't remember, the variance of x is just defined to be the expectation of x minus its expectation squared, which you can prove is equal to, using linear expectation, you can prove this is equal to the expectation of x squared minus the expectation of x whole squared. So what I mean here is like this is the parenthesization. Okay? And and since it's so simple, I'll prove Chebyshev. The probability that x deviates from its expectation in absolute value by more than t is the same as the probability that x, just square both sides of the inequality. X minus the expectation squared is bigger than t squared. And then now apply Markov. Markov, this is a non-negative random variable because it's something squared, so it's always non-negative. So by Markov, this is at most the expectation of x minus the expectation of x squared divided by t squared. But this is also known as the variance. Okay. So now let's look at some problems. The first problem that I want to look at is a problem known as approximate counting. So what's the problem here? I want to maintain a counter n subject to 3 operations. One is initialization. It just sets n to 0. 2 is increment. It just increments n by 1. And 3 is query. When you query, you should just return n. Actually, let me give the counter a different letter. Let's call the counter capital B. Actually, yeah, I'll just call that. Okay. So the naive algorithm is just maintain n in a single word. Since n is a number, since n is a number that's between 1 to n, this uses O of log n bits. In fact, it uses exactly log base 2 of n. It uses exactly log base 2 of n, which is O of log n bits of memory, to represent a number that's as big as n. Now, can we do better? And if all you know, let's say that all you know is that the final number is going to end up being between 1 and r, then yeah, you need log r bits of memory, right? Because by pigeonhole principle, if you use less than log r bits of memory, it means that 2 different numbers are mapping to the same memory state. And then you don't know, and then if you see that memory state, you don't know which of the 2 you have. So you don't really know the answer. Okay. However, we're going to settle for approximation, where we don't necessarily care that we know n exactly. We just want to know n up to, say, 1% error. We'll settle for knowing n not exactly, but just say up to some approximation factor. i.e., we just want to know some n hat such that n hat is, let's say, between n and alpha times n, where this alpha is what I'm calling the approximation factor. So if we only want to know that, then I don't need I don't necessarily need to use log n bits of memory, because I could do the following. In principle, I could then use less memory, because if all I know is that the answer is between 1 and r, let's look at the following numbers: 1, alpha, alpha squared, alpha cubed, all the way up to alpha to the log base alpha of r. Okay. If all I need to know is the answer up to a factor of alpha, then all I need to tell you is n is somewhere. Maybe n is right here. All I need to then tell you is the next power of alpha that's right after n. So I can just return this to you. And in fact, I don't need to return this number, because I know that I know that I'm always going to return a power of alpha. I can in fact just return the exponent. Right? So alpha cubed is definitely, in this picture, within a factor of alpha of n. So I only have log base alpha of r possibilities so maybe I can get away with log that number of bits. Log of log base alpha of r bits of memory, which is the same thing as, remember, if you think of alpha as being a constant, then this is O of log r bits. Or no, I think r is n. So basically what I'm saying is, if I only want to know the answer up to some approximation factor, like say alpha is 2, or say even alpha is 1.01, right? If alpha is 1.01, that means I want to know the answer up to a 1% error. I only, in principle, I can get away with only log n bits and be able to tell you n up to 1% error. Now, of course, the challenge here is, how do I actually achieve this with a streaming algorithm? Because yes, if I know n, then if I know n, I can round it to the nearest power of alpha, and then that will give me the exponent. But I don't know n, right? I'm a streaming algorithm. All I know is I keep getting these operations increment, increment, increment. And I don't know how many increments have happened so far. I mean, if I knew how many increments, how do I know how many increments have happened so far? I don't have a counter to store that number, because that would then take me log n bits of memory, and I'm trying to avoid using log n bits of memory, right? So is there a way to basically still use proportional to log n bits of memory without actually knowing n, right? Where I'm just operating in the streaming model where I just see these streaming increments coming in at me. Okay, so it turns out that the answer is yes. And before I show you why, you could then ask a similar question of, can I do better? Can I do better than log r bits? And or log of log base alpha of r bits? And the answer is no, not really. And notice I can't do better by more than a constant factor. In particular, maybe I can save like a bit, but not more than that. And the reason is, let's again look at all these powers. Now, let's just focus specifically on the case where the answer is either 1 or it's alpha squared, or it's, let's say, alpha cubed. How do I want to do this exactly? Let's just be a little, maybe it's 1 or it's alpha cubed or it's alpha to the 6th. I basically just take like every third one, I guess. Is that? Yeah, every third one. Then notice any answer I return for this is not a valid answer for any of the other box numbers because the box numbers are just so far apart from each other. They're not within alpha of each other. Okay. So that means my algorithm needs to have at least log base alpha of r over 3 different memory states. Because otherwise, 2 of these box things would have the same memory state, and I get the same answer, but that same answer can't be within alpha of 2 different box numbers. So that means I need to use at least log of log base alpha r over 3 bits, which is exactly log alpha of r minus O of 1 bits. So up to an additive 1 or 2 bits, I can't hope for better than log r. So let me actually just leave Chebyshev for now. So I'm going to show you an algorithm which is Morris's algorithm. Which stores a single number. It stores a number x, which is initially 0. And then when I do init, it stores x. Okay. When I do init, I set x to be 0. When I do increment, I do the following. With probability 1 over 2 to the x, x gets set to x plus 1. Otherwise, do nothing. Don't change x at all. And when I say query, I'm going to return 2 to the x minus 1. This is Morris's algorithm. And now let's analyze it. Okay. But before we analyze it, let me try and give you some intuition for why Morris is doing this thing. Okay. So remember, I'm trying to save memory. What's one thing I might do? One thing I can do instead of Morris is the following. I'll store some x initialized to 0. Every time someone says increment, I'll just flip a fair coin, 50-50. With probability 1/2, I'll actually increment x. And with probability 1/2, I'll do nothing. Okay. So, and then when someone says, what's n? What's the actual underlying counter? Well, half the time I incremented x and half the time I didn't in expectation. So I expect that x is roughly n over 2. So if someone asks me what's n, I'll just return 2 times x. Since x is approximately n over 2, 2 times x should be approximately n. Okay? So I kind of got away with something here, right? Because I was trying to store a number that was as big as n, and I got away with storing a number that's only roughly as big as n over 2, right? And n over 2 as a number is it takes 1 less bit to store than n. Okay. And Morris is basically taking this idea but being a little more extremely aggressive, right? Because I'm not trying to save 1 bit. I'm trying to like use exponentially fewer bits, right? So Morris is doing something similar. He's saying, look, this is what I'm going to do. I'm not just going to increment with probability 1/2. I'm going to increment with probability 1 over 2 to the x, which is a lot less likely. Okay. Since this is a lot less likely, I'm doing a lot less incrementing, which means the number I'm storing is probably much smaller, so I can get away with much less memory. So let's try to understand why this works. So the first claim, notice that x here is a random variable, right? Because I'm incrementing it in random ways as I run through the stream of increments. The first claim is that I can control the expectation of x. In particular, the expectation of 2 to the x is exactly n plus 1. Which now makes sense why Morris is returning this, because notice that the expectation then, if this is true, which it is, we'll see in a second, the expectation of 2 to the x minus 1 by linearity of expectation is equal to the expectation of 2 to the x minus 1, which is n plus 1 minus 1, which is n. So the return from the query is at least correct in expectation. Okay? So let's prove this. And let's denote xn is the value, let's call it xi, is the value of x after the first I increments. We'll prove by induction on n that the expectation of 2 to the xn is n plus 1 for all n. So the base case is that n is equal to 0, meaning we haven't done any increments yet. If we haven't done any increments yet, then x is 0. All we've done so far is initialize. So then 2 to the 0 is 1, which is 0 plus 1. So 2 to the x is then equal to 2 to the 0, which is equal to 0 plus 1. This here is n, so good. The base case checks out. Now let's do the inductive step. So we're going to assume that the inductive hypothesis is true for n and prove it for n plus 1. Notice that the expectation of 2 to the x n plus 1 is equal to the sum over j goes from 0 to infinity of the probability that xn is equal to j times the expectation of 2 to the xn plus 1, given that xn is equal to j. Okay? What is this? So this is the sum, j goes from 0 to infinity, of the probability that xn is equal to j, times, what is this conditional expectation? Well, with probability 1 over 2 to the x, we increment, otherwise we don't. So with probability 1 over 2 to the j, we increment, so now xn plus 1 is equal to j plus 1, so 2 to the j plus 1. And with the remaining probability, with probability 1 minus 1 over 2 to the j, xn plus 1 stays j, and then here we get times 2 to the j. So this is equal to now the sum j goes from 0 to infinity of the probability that xn is equal to j times, this is just 2, plus 2 to the j minus 1. Right? Because I have 2 to the j divided by 2 to the j is 1. So the 2 minus 1 is just a 1. So let's put a 1 here. Okay. So let's go to this board. So I have that what I said was expectation of 2 to the xn plus 1 is equal to the sum, j goes from 0 to infinity, of the probability that xn is equal to j times 1 plus 2 to the j. And I can write that as the sum probability that xn is equal to j plus the sum probability that xn is equal to j times 2 to the j. This, xn is some non-negative integer. So this is saying what's the probability that it's either equal to 0 or 1 or 2 or 3, etc. Well, that's 1. It's equal to something. This is just equal to 1. And this is, by definition, just equal to the expectation of 2 to the xn, which we know by the inductive hypothesis is equal to n plus 1. Therefore, overall, this expectation is equal to n plus 2, right? N plus 1 plus 1 is n plus 2, which is the same thing as n plus 1, which is what we wanted, right? The expectation of 2 to the xn plus 1 is equal to n plus 1 plus 1. That's exactly what we wanted to show with our induction, so we're done. So we bounded the expectation. But usually when I do these kind of approximation Monte Carlo algorithms, right, I don't just want to say that the output is, has some good property and expectation. I want to say that my algorithm works well with good probability, right? So for example, with Karger, I said, look, there's this parameter p, which is related to my confidence, right? With probability 1 minus p, I'm sure that my answer is right. And I could, I paid a log 1 over p there. And it was the same thing with Freyval's algorithm last lecture, where I could pay a log 1 over p and be confident with confidence 1 minus p that my answer is right. So here, we haven't talked about confidence yet, right? All we're basically saying is that the answer I return to the query is correct in expectation. I don't just want my answer to be correct in expectation. I want it to be correct with probability 1 minus p, because I want confidence. I want confidence in my answer. So good. We just saw that the expectation is right. We're going to get our confidence from Chebyshev. Okay. So in order to get the confidence from Chebyshev, I need to be able to bound the variance, right? Because Chebyshev says the probability that I deviate from my expectation depends on the variance. Okay. Good. So the variance, as I mentioned, for any random variable, the variance of y is equal to, I wrote it there, the expectation, well, I don't need to write it again. The variance of any random variable is the expectation of x squared minus the expectation of x squared. So this we know, right? This we know. In our case, this is just equal to n plus 1 squared, right? The expectation is n plus 1. I should be careful. This is not for us. Okay, so we care about, let me write it again. We care about y, which is our estimator. We care about y actually being 2 to the x. right? Because that's what we're basing our answer on. We know that the expectation of y is something that's helpful for us. It's n plus 1. The variance of y, by what's written there, is equal to the expectation of y squared minus the expectation of y squared. This we know is n plus 1 squared. This we don't know, right? So that's the thing that we need to bound now. So claim the expectation of 2 to the x squared, which is the same thing as 2 to the 2x, is equal to, and it's something funny looking, 3 halves n squared plus 3 halves n plus 1. Okay. So let's prove this. It's going to be very similar to the proof last time. So it's by induction on n. The base case is n equals 0. Then the expectation of 2 to the 2x is equal to 1, which is in fact equal to 3 halves times 0 squared plus 3 halves times 0 plus 1. So I'm happy. And now let's do the inductive step. And maybe I'll just start this and not finish it, because honestly, it's very similar to, it's very similar in technique to just this. It's just more computation. So I think I'll just start it. I'll start it off, and then if you want to see the precise computations, you can look in the notes which are on the website. So I want to bound expectation of 2 to the 2xn plus 1. And I'll write that as, now, instead of summing over all the possibilities for what xn is, I'll sum over all possibilities for what 2 to the xn is. So j goes from 0 to infinity of the probability that 2 to the xn is equal to j times the expectation of 2 to the 2xn plus 1, given that 2 to the xn is equal to j. Okay. And then this is equal to the sum over these j's, probability that 2 to the xn is equal to j, times, now what's this conditional expectation? So with probability, remember now, 2 to the xn is equal to j. So with probability 1 over j, we increment. With probability 1 minus 1 over j, we don't increment. If we do increment, so with probability 1 over j, this will become, right? This is the same thing as 2 to the x squared. So now, if we incremented x by 1, then 2 to the x doubled, right? If we increment x by 1, 2 to the x doubled, and then we squared it, so it quadrupled. So times 4j squared, right? Plus 1 minus 1 over j times j squared. And then if you just basically do this computation out, you'll get exactly what I promised you, which is this. Okay? Which again, I don't want to do on the board because it's not super interesting. But you can see it in the notes if you want the details. So that implies that at the end of the day, the variance of 2 to the x is equal to 3/2 n squared plus 3/2 n plus 1 minus n plus 1 squared, right? This is the expectation of y squared, and this is the square of the expectation of y. So this here is the same thing as n squared plus 2n plus 1. So if I subtract this from that, at the end of the day, what I get is 1/2 n squared minus 1/2 n, and that's it. So this is equal to 1/2 n minus 1. Okay. So this implies now that if I use Chebyshev, the probability that the answer to query minus the actual true answer. So this, n hat is basically what, let me say, n hat is by definition my estimate of n, which was 2 to the x plus 1, or 2 to the x minus 1. We know that n hat, in expectation, n hat is n. We know that. The variance of n hat is the same as the variance of n, right? Sorry, the variant of n hat is the same as the variance of 2 to the x. Because if you take a random variable and you translate it, that doesn't change the variance. So the probability that n hat minus n is bigger than, let's say, epsilon times n is at most the variance of n hat over epsilon squared n squared. And the variance we said over here is equal to 1/2. It's less than 1/2 n squared over epsilon squared n squared. So the n squareds cancel. And if epsilon is not too small, let's say, for example, if epsilon is like 0.9, this is less than 1 over 0.9 squared times 1/2, which is some constant. 1 over 0.9 squared is roughly the same as, so 1 over 0.9 is like, 0.9 is 9/10. 1 over 0.9 is 10/9, right? 10/9 is roughly 1.1. It's 1.1111. If you square it, you get roughly 1.2. So this is roughly, let's say, 1.2 times 1/2. Here I'm assuming, let's say, that epsilon is like 0.9, which isn't great. So this, this here is, it's certainly bigger than 1/3. So this isn't that good. What it's saying is, with probability at least 1/3, which is it's not tiny, but it's not that great either. With probability at least 1/3, I'll get an answer that's within 90% of the true answer. Okay, so like if the true answer is 100, I promise you that I'll tell you something that's between 10 and 190. So at least, I'm within a factor. I'm basically within a factor of like 10 of the true answer, which is not great. How can I do better? So let's do better. So a fact from probability, maybe you've seen it in 170, if A and B are independent, then the variance of A plus B, so this is fact 1, the variance of A plus B is the same as the variance of A plus the variance of B. So this, unlike linearity of expectation, you can only say that the variance of the sum is the sum of the variances when they're independent. And fact 2 is that the variance of, let's say, a scalar times a random variable is equal to A squared times the variance of that random variable. So it's not linear like expectation, where if you multiply by a scalar, you can just pull it out. Here, when you multiply by a scalar, you have to pull out the square of that scalar for the variance. This just follows from the definition. So we can use these two things to do better as follows. So what we'll do is we'll run Morris's algorithm Q times in parallel, each making independent random decisions. Okay. This will give us estimates n1 hat, n2 hat, up to nq hat. Our new estimate will just be their average. And I'll call that n star, which is just 1 over q times the sum of ni hat. I goes from 1 to q. Notice that the expectation of n star is still, by linearity of expectation, it's still the right thing. It's still n. And the variance of n star, now because we're running these parallel copies of Morris with independent randomness, the variance of the sum is the same as the sum of the variances. So the variance of n star is equal to the sum I goes from 1 to q of the variance of ni hat over q, which by fact 2 is 1 over q squared. When you have a scalar, you pull out the square of the scalar, times the sum I goes 1 from 1 to q of the variance of ni hat, which we know from last time, the variance of ni hat is at most 1/2 n squared. So that's at most basically n squared over 2q squared. So if we just run the algorithm q times in parallel, that's going to use q times as much memory, because there are q copies of the algorithm running side by side, so there's q times the memory. But at the same time, we get to improve the variance by a q squared factor. What does that mean now for the approximation guarantee of the algorithm? So now the probability that n star minus n is bigger than epsilon n is at most the variance of n star divided by epsilon squared n squared, which we know is less than n squared over 2q squared times epsilon squared n squared. The n squareds cancel. And now if I set, I just realized something, which is that, so I have a 1 over q squared here, but I'm summing up these variances q times. So it's variance of n1 hat plus variance of n2 hat plus variance of n3 hat. There are q of them. So I should have actually multiplied this by q. So this q cancels that squared. So this is actually equal to n squared over 2q. Yeah. So if I average q copies, I get to decrease the variance by a factor of q, not q squared. So this is q, not q squared. And then what I do is I can set q to be equal to, for example, 1 over 2, well, let's say p. Yeah, 1 over, okay, so 1 over 2 epsilon squared p ceiling. I'll just set q to be that. Then the 2 cancels, the epsilon squared cancels, and then this is basically less than or equal to p. Okay. So overall, I need q, which is O of 1 over epsilon squared p copies. So the memory blows up by this amount. And what's the memory per copy? Well, let's look at it like this. Once I've had n increments, so basically, yeah, so x is this counter I'm storing in memory. Once x gets to be something like as big as, let's say 3 log n, once x gets to be as big as 3 log n, the probability that I increment x in a future increment to n is at most 1 over n cubed, right? And there are only ever n increments ever, so the probability that I ever increment it again is at most 1 over n cubed times n, which is 1 over n squared. So it's once x gets to be big enough, once x gets to be some constant times log n, it's very unlikely that I'll ever increment it again. So note, with high probability, x is less than, let's say, 3 log n always, implies I can store x using at most log base 2 of 3 log n, say log base 2, 3 log n, which is O of log n bits. So I can get a total memory which is with high probability at most O of log n over epsilon squared p. Okay. Now this gives you something, right? Now the nice thing about this compared to that I basically was forced to set epsilon to be 0.9, right? I couldn't make epsilon be too small, otherwise the right-hand side would be bigger than 1 and I would get nothing. Here, I allow epsilon to be a user-stated parameter. And basically, if you want good epsilon, meaning you want to really know the answer up to 1 plus epsilon and multiplicative error, you can do it. You just need to increase your space by running more parallel copies. Okay. Now, is that dependence on epsilon and p optimal? And the answer is no, it's not optimal. You can actually do better. And I won't give you the analysis, the full details of the analysis for why you can do better, but I'll give you a hint as to how it works. So doing better. So, there are a couple of algorithms. One is the trivial algorithm, which is you increment x with probability 1. Okay, so you store this counter x. Whenever someone says increment to n, you increment x with probability 1. So x is, in other words, x is just a counter that stores n. What we did now, Morse's basic approach, is that you increment x with probability 1 over 0.5 to the x, 1/2 to the x. What are the pros and cons of these approaches? The pro is that you only need log n memory. The con is that you have high variance. Meanwhile here, the pro is that you have low variance. In fact, here you have 0 variance. The con is that you're actually using more memory. You're using log n bits of memory, whereas here you're only using log n. So the idea is, why don't we do something in between? Increment x with probability not 1 to the x. So this is basically 1 to the, 1 is the same thing as 1 to the x, right? So instead of incrementing with probability 1 to the x, instead of incrementing with probability 0.5 to the x, we'll increment x with probability, let's say, very close to 1, but not exactly 1. 1 minus eta to the x. So now, kind of intuitively, it makes sense. The variance, it's not going to be 0 anymore because there is something probabilistic happening here. But it's very close, the probability increment is so close to 1 that the variance should at least be better than this. At the same time, the memory I expect to be somewhere, I'm not always incrementing. So the number I'm storing is going to be smaller. So my memory should be better than this. But I am incrementing more than this algorithm, so the memory should be in between. And what you can show is, if you choose eta to be something proportional to epsilon squared times p, then it gives you exactly what you want. You can prove that if you do that, you'll have an estimator such that the probability that you deviate from the answer by more than epsilon n will be at most p, exactly what you want. And you can prove that your space complexity will be something like O of log n plus log 1 over epsilon plus log 1 over p bits. Okay? And of course, here to estimate n, you just output x. Here to estimate n, you output 2 to the x minus 1. Here, it's going to be something different that depends on eta. You have to do a calculation basically to figure out what exactly it should be. But you can make that work out. I'm not going to do that on the board today. Okay? So that's all I wanted to say about Morse's algorithm. And we do still have some time left. And I want to talk to you about one more algorithm, which is the distinct elements problem. It's an algorithm for the distinct elements problem. So problem 2 is distinct elements. So the input here is just a stream of items. Let's say they're integers, I1, I2, Im. Each integers in the range from 1 to n. And the goal is to output the number of distinct elements. So if you treat if you look at the set of all the things that appeared, what was the size of the set? For example, if the stream were like 1, 7, 7, 2, 1, The distinct elements are 1, 7, and 2, so this should return 3. Okay. Why might I want something like this? I just want to do some kind of data analytics. How many distinct users watched my video on YouTube, where I measure a user by their IP address, right? How many distinct, what's the size of my vocabulary? So you look at all the writings of Shakespeare, and you go through and you just ask, how many distinct words did Shakespeare use across all of his plays? And this is really not a toy example, not the Shakespeare thing, but this problem is really not a toy problem. If you just Google things like hyperlog, that's an algorithm that's kind of an industry standard for solving the distinct elements problem. There are a ton of people at at big companies, at the Googles and the Amazons and the Yahoos, et cetera, that are using algorithms that solve the distinct elements problem. This is something that comes up a lot in applications. Okay. So what are the naive algorithms? You could say, you haven't learned hash tables yet. You're going to learn them in 2 lectures. But you could say, well, why don't I just throw all the numbers in the hash table, and then whenever I see a new number, if it's already in the hash table, then I don't need to count it. If it's not in the hash table, I'll add 1 and I'll put it in the hash table, right? So basically the size of my hash table is the answer. It's like the number of distinct things I saw. The problem with that is, well, what if everything you saw was distinct? What if there were no repeats? Then your memory consumption is proportional to the size of the database, right? You actually are remembering everything. And the whole point of streaming is to not remember everything. You're trying to use memory that's much less than what seems to be the required memory, right? So for example, with Morris's algorithm, even though naively you needed log n bits of memory, we got away with log n bits of memory, which is like exponentially better. And that's the same kind of thing we want to do here. Naively, you might need to remember all m things. That would take m memory. I want to get away with like log m memory. Or naively I could say, look, there are only n possible numbers I could ever see because all the numbers are between 1 and n. I'll just remember a bit vector of length n, and each bit in that bit vector will just tell me, have I seen item I or not, 0 or 1? And then at the end of the day, when someone queries, I can then just look through and see how many 1s there were, and that'll tell me the answer. So that's n bits of memory. And I would like to get away with log n bits of memory, right? So I'm trying to get away with like exponentially better memory. Okay. So let's see an algorithm for the distinct elements problem. And it's going to be, at first what I'll show you is an idealized algorithm, meaning there are problems if you try to implement this algorithm. But let's just, let's ignore those problems for now and just look at the algorithm and analyze it. And then we'll talk a little bit at the end of lecture about how you would fix those problems. So what I'll do is I'll pick a random function h, which maps my universe of all possible items into the continuous interval from 0 to 1. And then what I'll do is I'll initialize some counter x to b1. And then for each I in the stream, I'll set x to be the min of what it was before and h of I. And then when someone says query, I'll return 1 over x minus 1. Okay. Now, what are the problems with this algorithm? Notice that when I pick this random function h, I need to remember what function I picked, right? Because later I need to keep evaluating h as I see items in the stream, and if I see item 7 now, or I see item 1 now, and I see item 1 again later, then my h of 1 had better be consistent, right? Because I'm imagining here that there's an actual function h that I'm using throughout the algorithm. So the h of 1 I see in the past had better be the same as the h of 1 I see later. So I need to actually remember h. Naively to remember h, well, there's h of 1, there's h of 2, there's h of 3, there's all the way up to h of n. There are n numbers there. So naively to remember h, I need to remember n numbers, which is n memory, which is pointless because there's already a very simple algorithm that uses n memory, namely that bit vector thing I told you about. And not only am I using n memory, but it's not even n bits. It's n continuous real numbers. Computers can't store continuous real numbers. Computers can only store bits. So, I would have to maybe discretize this into a fine enough discretization and prove that the algorithm would still work. But now it's even more than n bits of memory, whereas there's already a very simple algorithm that works that uses n bits of memory. So that's like kind of the main issue. Actually, those two issues are really the main issues that make me call this an idealized algorithm and not the final algorithm, but this algorithm is fixable. And kind of everything I'm going to talk about with this algorithm is really due to Flageolet and Martin. Martin is his last name, and Flageolet is also his last name, back in 1983. Okay. Now, before we analyze this rigorously, I want to give you an idea of what's happening. So let's say T is the actual number of distinct elements. And now what we're doing here is we're keeping track of the smallest, there are T random numbers here, right? There's like h of the first element, h of the second, up to h of the tth distinct element. Those are just T independent random numbers. So we have this continuous interval from 0 to 1. We have T random numbers independent that are being dropped onto this interval. Let's say T is 4. So we have 4 random numbers on this interval. Imagine there was one random number on the interval. Imagine that T is 1. If T were 1, kind of in expectation, where would you expect a random number between 0 and 1 to be? You'd expect it to be in the middle. What if you had 4 random numbers? Well, we'll prove this. You expect them to basically be evenly spaced throughout the interval, meaning that the smallest one would be a fifth, the next smallest would be 2/5, 3/5, and then 4/5. That's the expectation. You can prove that. So what are we keeping track of? We're keeping track of the minimum of these T random numbers. So, we expect that the minimum of T independent random numbers, random uniform 0, 1 numbers, would be 1 over T plus 1. But what is it that we want to know? We want to know T. So we have this number x, which we expect to be 1 over T plus 1. So we invert it. So we get T plus 1. We subtract 1, so we get T, right? So we're basically trying to set up some kind of game here so that we have some random variable we're storing such that from that random variable, we can kind of using expectations, recover the quantity we actually want to recover. Okay. So let's make this, let's do a little bit of math here just to show that this thing works out. So claim 1. Claim 1 is that the expectation of x is indeed 1 over T plus 1. So proof. So if you haven't seen this before, if you haven't worked a lot with continuous random variables, let me just tell you a little fact here, which is that if you have a non-negative random variable, that implies that the expectation of x is equal to the integral of the probability that x is bigger than, I don't know, give me a letter, lambda d lambda, I guess. Or let's say y dy, when this integral goes from 0 to infinity. Okay. So that's kind of a fact that we'll use. In discrete random variables, it's very similar to like if you have a non-negative random variable, the expectation of x is equal to the sum over all non-negative random variables, or all integers, sorry, all non-negative integers of the probability that x is bigger than y, where like y just ranges over all non-negative integers. But the same is true for continuous random variables. Okay. So we know then that this is a non-negative random variable, right? It's definitely between 0 and 1. So the expectation of x is equal to the integral of, actually, let me just write here, like basically at the end of the day, I'm basically saying that x is the min of x1 up to xt, right? Where like these are the hashes, these are the function evaluations h evaluated on the t distinct elements. So the expectation of x is equal to the probability, integral from 0 to 1, of the probability that x is bigger than y dy. This is equal to the integral from 0 to 1 of the probability that for all I going from 1 to t, xi is bigger than y, right? X is the min of all the xi's. So what does it mean that the min of all the xi's is bigger than y? It means all the xi's are bigger than y. And the xi's are independent random variables. So this is exactly equal to the integral from 0 to 1 of the probability that, say, like x1 is bigger than y, raised to the tth power dy, because they're independent. You have a continuous random variable between 0 and 1. What's the probability that it's bigger than y? 1 minus y, right? Here you have 0. Here you have 1. You have this continuous random variable between 0 and 1. What's the probability? There's y. What's the probability that it's in the shaded region, namely that it's bigger than y? It's exactly 1 minus y, the length of the shaded region. Okay. So this is equal to the integral of 1 minus y to the t dy from 0 to 1. Okay. And then you can do a u substitution, right? Just set like u to be 1 minus y, which implies that dy is equal to minus du. So this is equal to the integral from 0 to 1 now. So u now goes from 1 to 0, and there's a minus sign. So I can get rid of the minus sign and make it go from 0 to 1 again. Of u to the t du, which is exactly u to the t plus 1 over t plus 1, going from here 1 to 0, which is exactly 1 over t plus 1. Okay, so that's exactly what I wanted. Okay. So the expectation is exactly as I said. And remember, how do these things usually go? When you set up some kind of estimator that's unbiased and has the correct expectation, the next thing you want to know is it not only does it have the right expectation, but is it close to its expectation with good probability? Namely, can we bound the variance? And then we can do the same thing we did for Morris and plug that into Chebyshev. So let's try to understand that. So again, the variance of x is equal to the expectation of x squared minus the expectation of x squared. So let's try to understand that. So claim 2 is that the expectation of x squared is, let's figure out what it is. So proof, the expectation of x squared, again, we can say that's equal to the integral from 0 to 1 of the probability that x squared is bigger than y dy, which is the same thing as the probability that x is bigger than the square root of y. And using the same reasoning as there, that's equal to the integral from 0 to 1 of 1 minus square root of y to the t dt dy. And then you can again basically do a u substitution. Let me not, this is just purely computation. If you want to see details again, you can look at the lecture notes. This integral comes out to what? It comes out to 2 over t plus 1, t plus 2. Okay? That's just a computation. So that's that. 2 over t plus 1, t plus 2. So that implies that the variance is equal to 2 over t plus 1, t plus 2, minus 1 over t plus 1 squared. Okay. Now let's give things similar denominators. So let's multiply this by t over 2, by t plus 2 over t plus 2. Let's multiply this by t plus 1 over t plus 1. This is equal to 2t plus 1 minus t plus 2 over t plus 1 squared t plus 2. The numerator is 2t plus 2 minus t minus 2. So this is exactly equal to t over t plus 2 times 1 over t plus 1 squared. Okay. And really the takeaway is that this is less than, t over t plus 2 is less than 1. So this is less than the expectation of x squared. Right? The expectation of x is 1 over t plus 1. Here we have 1 over t plus 1 squared times something less than 1. So what will we do next? We'll run q copies of this algorithm in parallel with independent randomness to get x, sorry, so I guess let's call this, yeah, unfortunately, so there's these xi's and then there's xi's I want to get there. So to get counters, let's call them x1 up to xq. So this x1 is like in the first parallel run of the algorithm, the min of all those function evaluations. X2 is in the second parallel run of the algorithm, the min of all those function evaluations, etc. And then we'll set x star to be the average of these, 1 over q times the sum xi. I goes from 1 to q. And then query will return 1 over x star minus 1. So what's the probability that x star minus 1 over t plus 1 is bigger than epsilon over t plus 1? This is less than t plus 1 squared over epsilon squared times the variance. Remember, the variance gets divided by q because we averaged q copies. And we know that the variance of one copy, the variance of one copy was less than 1 over t plus 1 squared. So it's 1 over t plus 1 squared times 1 over q. And then now we get some nice cancellations. This cancels that. And then I can make sure that this is less than p by setting q to be, again, 1 over epsilon squared p. Okay. So the total memory is basically O of 1 over epsilon squared p. Because each parallel run of the algorithm uses constant memory, I only have to remember one counter, which is x. I'm assuming, again, that h is, I'm not taking into account the memory required to store h, because that would be a disaster. But my total memory is this, which notice doesn't even depend on n. It's magic. Right? It just depends on the desired confidence and approximation guarantee. Now, I don't want to talk about how to make this idealized algorithm a non-idealized one. I won't have time for that. But I do want to say a little bit about it. First, there's an alternate algorithm, alternate way to get 1 plus epsilon error, besides averaging. Right there, I just averaged q copies in parallel. Another way to do it, which is actually due to Bar Yosef and others in 2002, is the following observation. Look, we're just storing the minimum hash value. Okay, that's only 1 unit of memory. But the minimum hash value, it has a lot of variance. So basically we have these t random numbers, and I'm saying just look at the smallest of the t. What you can actually prove, which is kind of intuitive, is that the median of these t random numbers is actually very concentrated, right? So, like for example, let's say that I flip, a million random. I get a million random numbers, each independent between 0 and 1, and I ask you, what's the number that's the 500,000th smallest number? So it's the number that's right in the middle in sorted order. I would expect that number is really, really close to 1/2 with really, really high probability. Okay. Now, if I wanted to store the median hash value, though, there are these t numbers. If I want to store the median of these t numbers, I need to keep track of basically the bottom t over 2 numbers. So I would use memory proportional to t over 2, which is, again, proportional to t. I don't want to use memory proportional to t. So they say, okay, let's not do the median because that's too much memory. But let's try to store the kth, not just the smallest, but let's try to store the kth smallest hash value. So that's going to use k memory. So store the k smallest hash values. Call them like y1 is less than y2 is less than yk. So this is the kth smallest hash value. And let's return k over yk minus 1. Basically, the expectation of yk, you can prove, is k over t plus 1. So I'll basically invert it, multiply by k to kill the k, and subtract 1. And this, they showed, can be de-randomized, can basically be implemented in a non-idealized way. First of all, 1 can pick like capital N to be like, let's say, little n cubed, and discretize the continuous interval 0, 1 to being like multiples of 1 over n. So 0, 1 over n, 2 over n, up to like n minus 1 over n, and then like 1. Okay, so now we don't have to deal with continuous numbers. We just have to deal with like integer multiple, basically integers. And 2, when we say that h is a random function, what we really mean is like define the function h all, which is the set of all functions mapping 1 to n into 1 up to capital N. That's h all. And notice that the size of h all is basically capital N to the lowercase n. The number of functions mapping 1 to little n into the range 1 to capital N is exactly capital N to little n. And identifying any function in this set takes log the size of the set bits. So what you're going to see in 2 lectures when Professor Chiesa talks about hashing is that kind of one of the keys things in like designing in hash functions is basically showing that for a lot of applications, like for example in universal hashing, you can get away with a set of functions that's much smaller than h all. You don't really need the set of all functions. You can instead of like the set of all functions at exponential size. In many applications, it's actually possible to come up with a set of functions that only has polynomial size. So identifying a random function in that set of functions only takes log of polynomial bits, which is log n bits. And that's exactly the case here. What Bar-Yosef et al. Showed is that this h here doesn't have to be a truly random function. It suffices for little h to be a random function drawn from a universal hash family. And I'm not going to talk, we're done with lecture today, so I'm not going to tell you what that is, but you'll see that in 2 lectures when Professor Chiesa talks to you about hashing. Okay? And that basically lets you implement this algorithm in very little memory. Basically, little h will only take you log n bits of memory. And overall, this algorithm will give you, and basically I should say that k will end up being something like 1 over epsilon squared. So you need to store you need to store these k numbers. Each one takes log n bits. Overall, your memory is 1 over epsilon squared times log n bits. So overall, 1 over epsilon squared plus log n bits. I should mention that the optimal bound turns out to actually be times log n bits, sorry. Because you have 1 over epsilon squared numbers, each one takes log n bits, so 1 over epsilon squared times log n bits. It's actually possible to achieve plus log n bits. And that's an algorithm due to Daniel Kane, myself, and David Woodruff. That's something I did back in my PhD thesis a decade ago, back in 2010. And you can prove that that's actually optimal. There's no way to do better. Good. So that's all I have for you today for streaming. And if you want to learn more streaming, take my course in the fall, CS294-165. Okay, thanks.